So on today's episode of Code with Senpai, we'll be solving the unique paths problem asked by these companies. So the problem states, if we're given a grid and we can only go right or down, how many unique paths are there to get from the start to the end? So how would you solve this on paper? Well, if we're given a grid of 2 rows and 3 columns, from this cell, we can get to the end by going right, down, right, or down, right. 3 paths. From here, we can go right, down, or down, right. That's 2. From here, we can only go down, and from here, we can only go right. So a pattern that you might notice here is that we were able to sort of pre-fill this last row and the last column with 1 because we can only go that one direction from there. And then for the other cells, we can get that answer by taking the sum of the cells from the bottom and the right. So 1 plus 1 is 2, and 1 plus 2 is 3. So the fact that we were able to compute this overall solution by solving the smaller subproblems that lead up to it lends to a dynamic programming solution, where each cell is going to represent the number of unique paths from that cell to the end. So we can represent this recurrence relation as the current cell is going to be equal to the cell from the bottom plus the cell to the right. And it also helps that, this problem, it uses a grid and you're trying to find this maximum, which should also point you to a dynamic programming solution. So if we were given a bigger grid, how would we fill this out? So a 3 by 3 grid, and it should be pretty mechanical, right? So we know we can pre-fill these with 1s, and then from here we can go 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, and 3 plus 3 is 6, where 6 is the final answer in a 3 by 3 grid. So when we're actually coding this, it helps to add some padding to the end, like this. And then we can change this a little bit to add a plus sign here, and then we can zero these out. And then use this following equation to get the whole grid. So if we're going to start here, and then 1 plus 0 is 1, and then 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 0 is 1, 2 plus 1 is 3, and 3 plus 3 is 6. So you'll see that I like to iterate backwards here. A lot of people like to do this problem going from the start to the end, but I think doing it in reverse helps with the follow-up by making the code a lot cleaner. So yeah, but it doesn't really matter as long as you get the main intuition of the problem. So the running time and space complexity of the solution is going to be equal to the big O of the number of rows times the number of columns, because we gotta iterate through the whole grid and store the results as we go. All right, so let's see some code. So we take our first example of a grid with 2 rows and 3 columns. We're going to initialize our DP table. And I'm going to import NumPy here so we can visualize this a little easier. Like that. So like I said, we're going to add some padding now to handle the out of bounds cases. And we're going to pre-fill our first result, where we know the answer is going to be at least 1. And from there, we just iterate backwards. Where the answer to the current cell is going to be the sum of the cells from the bottom plus the right. We print our final result. All Our answer is in the first cell. 3, yep. And that's what we expect. So it's in here. Get rid of our logs. Make sure that we return the answer. And then just like that. And there it is. So the follow-up question asks, what if there are some obstacles added to the grid? So that's saying, like, if we took the grid that we had before and we placed a rock right here in the middle. So what would change here? Well, it would sort of block out or zero out the paths that go through that cell, right? So if we were to recompute these and we were to count the obstacle as a 0, if we go 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2. Because, like, as you can see, from this cell to get to the end, if there's an obstacle in the center, now we can only go right, right, down, down, or down, down, right, right, which is 2. All right, so let's see some code. Well, if we take exactly what we had before, the difference now is that we don't know the number of rows and columns, right? But we can figure those out by looking at the dimensions of the obstacle grid. So just like this, right? Now the main difference is that, well, if there is an obstacle at that spot, then we're not going to compute it, right? We're just going to take the 0 because we can't go through it. So in this problem, an obstacle in the obstacle grid is marked by a 1, okay? So we're only going to do our math if there's no obstacle there, right? So if you look at that cell, if there's no obstacle, then we can sum it up. So just like that. And just make sure that we're looking at the same row and column here. And that's it. You can check out the code in the description below with more details about this problem. If you found this video helpful, please like, subscribe, comment, and share with your friends. And feel free to donate. If there's any other problem that you'd like me to go over, please let me know. And thanks for watching.